All right. Hello there, everybody. Today we are going to be looking at an extra section. So this section is not a section you have to complete. It is related to some stuff we did in chapter 4, which was solving equations. The difference today is that we have equations that we can't just jump right in and solve. We need one of our identities for. So you will need your formula sheet if you are choosing to go through this section that we've been using through chapter 6. But basically, when you look at your equation, you can't start solving right away. You're going to have to look and see, do I have any identities here that I need to replace? And then I'm going to start solving from there. The other thing we need to check when we solve our equations is for any non-permissible values. So if we are dealing with any of the reciprocal identities, or if we are solving an equation that has a fraction in it somewhere, we need to always check for non-permissible values as well, and check that one of our answers is not also a non-permissible value. If we do get an answer that's a non-permissible value, we consider that extraneous. Similar to Precalculus 11, you had some extraneous answers when you did rationals. And so we're going to be checking for non-permissible values today as well, if necessary. So this first question here, we have no fractions. Therefore, we have no non-permissible values. We're also going to take a look at the domain we've been given, which is one cycle. Okay, from 0 to 2 pi. So we don't need to write this in a general form. We just need to find out how many answers we have going around one cycle. Okay, and we can also see here that we have one identity. We have cosine 2x. So the tough part people find here is, well, for cosine 2x, there are 3 options. We have one option that just has cosines, one that just has sines, and one that has both a cosine and a sine in it. And because if we look at the rest of our equation here, we have a 1 and a cosine. So I don't want to be adding sine to the mix here. That's going to make it harder to solve, not easier. So I'm going to pick the identity from my formula sheet for cosine 2x that only has cosines, which is 2 cosine squared x minus 1. That's the identity we want. If we pick one of the other ones, what we're going to have to do is we're going to end up having to replace the signs anyways with something else. So it's not incorrect, it's just more work for us. So we always want to be working in our equation with only sines or only cosines, if at all possible. So that's why I'm picking the only cosine one here. I still have a plus 1 and a minus cosine x. I haven't done anything with those. And I still have equals 0. Now we don't really need the brackets here. We can rewrite this without the brackets, but we can see that we have a minus 1 and a plus 1. So those are going to cancel out. And I'm going to end up with 2 cosine squared x minus cosine x equals 0. Now, a reminder from chapter 4, anytime you see something squared, you're going to treat it like a quadratic because it is. And we're going to factor. So what we can factor here is a cosine out of both of these terms. If we do that, our first term is left with a 2 and still a cosine. And the second term, if I factor out cosine, I end up with minus 1 equals 0. So now this means we either have cosine x equals 0, or we have 2 cosine x minus 1 equals 0, which means for this second factor, this means that we would have 2 cosine x equals 1, or cosine x equals 1/2. So some of you might do that in your head and not need to go through all those steps there. That's fine. So for our left-hand one, cosine x equals 0, if I go back to my quadrant system from chapter 4, I know that cosine x equals 0 on the y-axis. So this first one would be if x is equal to pi over 2. And the second one would be if x is equal to 3 pi over 2. So pi over 2 is that first answer. 3 pi over 2 is the second answer. For cosine x is equal to 1/2, we know that that means cosine is positive, which is in quadrant 1 or quadrant 4. And we know that cosine is adjacent over hypotenuse. And we know for one of these triangles, our third side is root 3, which means our reference angle here is pi over 3. And I'm using pi over 3, not 60 degrees, because of the domain in the question. The domain is in radians. My answer should be in radians. So this means that in quadrant 1, my answer would be pi over 3. And in quadrant 4, my answer would be 5 pi over 3. So I have 4 answers here for this quadratic. And remember that that can happen. We can have up to 4 answers. Okay. Next one. Again, we have to look and see where we have an identity. The 3 sine x, definitely not an identity. But if you take a look at 1 minus cosine squared x, what does this look like? Well, this is the same as sine squared x from our Pythagorean identity. So we can rewrite this as sine squared x equals 3 sine x minus 2. And now, again, we have all signs, so we can start solving like chapter 4. From here on, this is just chapter 4 stuff. The new chapter 6 stuff is recognizing the identities and replacing those so that we can proceed like chapter 4. So once we have a quadratic, we move everything to one side. I'm going to move everything to the left because I like my squared term to be positive. And then I need to factor. So this means that we either have sine x equals 2 or we have sine x equals 1. Now remember from our graphs in chapter 5 and from our knowledge of sine being opposite over hypotenuse from grade 10, we know that the biggest value sine x can have is 1. So we can't have sine x equals 2 because that would mean our opposite is bigger than our hypotenuse, which makes no sense. So this is no solutions for the first one. That one's not possible. Okay. The second one, again, where does sine x equal 1? Well, sine x equals 1 on the positive y-axis, which means that x is equal to pi over 2. So we only have one solution for this one. And again, we would need to check if we have any non-permissible values. There's no fractions in this question, so there are no non-permissible values that we need to consider. All right, this one is a little different. It's giving us a domain of degrees, so our answer is going to be in degrees. Okay. For this question, we do have a fraction. We have a cotangent. So we're going to change our cotangent so that it's in terms of sine and cosine. And this is going to lead to some non-permissible values here. We know that sine x cannot equal 0 because it's on the bottom of a fraction. So the question is, where is sine x equal to 0? Sine x is equal to 0 on the x-axis. So 0, pi, 2 pi, or because we're in degrees, 0, 180, 360. Okay. So this means that x cannot equal 0 degrees or 180 degrees. I'm not including the 360 because if I look at my domain in the question, it does not say or equal to. So right here, we're not including 360. Okay. So if one of these is one of my answers, we're not actually going to include it because it's a non-permissible value. Okay. Once we've done that, we can keep going. We notice that we have a sine and a sine on the right side. These will cancel out. And we end up with cosine squared x equals cosine x. We have all cosines. We can proceed like chapter 4. It's a quadratic. We want to move everything to one side and factor. So I'm going to move to the left because I like my squared term to be positive. Now I've got a cosine in both my terms. I'm going to factor a cosine out, leaving me with cosine minus 1. And this means I either have cosine is equal to 0 or I have cosine is equal to 1. Again, we know cosine is equal to 0 on the y-axis. So this would be x is pi over 2 or 90 degrees because our question's in degrees, or x is 3 pi over 2 or 270 degrees. Cosine x is equal to 1 on the positive x-axis, which means that x would be equal to 0 degrees or 360 degrees. But again, we're not going to include 360 because of our domain. We just said we weren't including 360 because it's not less than or equal to, it's just less than. And we're not going to include 0 degrees because this is a non-permissible value. So this one's not included, which means our final answer is just that x is equal to 90 degrees or 270 degrees. So we didn't actually get to keep any of our answers from our second factor there. Next one. Again, I need to check and see if I have any identities because I've got a sine and a cosine, and it's not a regular sine, it's a special sign because of the 2 inside. But I do know that this is an identity. This is 2 sine x cosine x. So I'm going to replace that. Now, the problem that I have here is that I don't have a quadratic and I have no way I can really get rid of sines or cosines. What a lot of people will do for this question is they will divide both sides by a cosine. The problem is, like with quadratic questions, if you simply divide, you're missing the answers that go with that thing you divided by. So what I actually want to do is move everything to one side and factor the cosine out. If I divide by cosine, I'm going to miss answers that go with the cosine. So I'm going to move everything to the left. It doesn't matter which side you move things to. And now I'm going to factor the cosine out. Now I have two factors. Cosine x could be 0, or this big giant gross 2 sine x minus root 2 could be 0. And then if I solve this second factor, I get sine x is root 2 over 2. Now, just a reminder again from chapter 4, sine x being root 2 over 2 is the same as saying 1 over root 2, which will be more helpful for special triangles. Okay, so let's start with the cosine equals 0. Cosine again is 0 on the y-axis. Okay, it asked us to give a general solution in radians. So general solution means we need the plus 2 pi n since we're in radians. Oh dear. Where n is an integer. Okay. So for the cosine answer, we have pi over 2 for the top and 3 pi over 2 for the bottom. So we can either write this as pi over 2 plus 2 pi n, where n is an integer, and have a second answer, Or if you'll notice, because these are 180 degrees apart or pi radians apart, we could write this as one giant answer that is pi over 2 plus pi n. Because to get from one to the other, we only have to add 180 degrees each time. Either answer is fine. The second one is considered a little bit more simple, but either one would work. Okay. For our sine factor, we have sine is positive, so we're in quadrant 1 or quadrant 2. If I rewrite this, it's part of my special triangles where my opposite is 1, my hypotenuse is root 2, which makes my other side 1 as well, and my reference angle pi over 4. This means in quadrant 1, x would be pi over 4 plus 2 pi n. And in quadrant 2, x would be 3 pi over 4 plus 2 pi n. We can't do the trick we used on the other factor because there's no way you can add 180 degrees to get from one of these arms to the other. If we added 180 degrees to the quadrant 1 angle, we would end up in quadrant 3. We would end up down here, which we don't. So we have to write these as two separate options. But for the cosine x equals 0 solutions, either one works. You can give it as two answers where you add a whole circle each time, or you can combine it into one answer where you add a half circle to get from one answer to the other. Okay. This one's a bit trickier because you cannot write it in just sine or just cosine. You have to be able to work with both. And you have to be able to notice that this is true over here. Okay. All right, let's try another one. Again, we've got general solution in radians. So this is going to be plus 2 pi n. Again. Okay. Right now we have a problem. We don't have just sines or just cosines. We have this cosecant. So I want to rewrite this as 3 over sine x. Now I have a fraction. So again, I have non-permissible values I need to consider. Sine x can't be 0. It's on the bottom of a fraction. And again, we know that sine x is 0 on the x-axis. So this means x can't equal 0, pi, 2 pi, etc. It can't be pi n. So if we get 0, pi, 2 pi, etc. as one of our solutions, we're not going to include it because that's a non-permissible value. Now, the problem here is that we have a fraction. I don't want to deal with a fraction. So what I'm going to do is I'm going to multiply everything by sine x. When I do that, I end up with 2 sine squared x equals 7 sine x minus 3. Okay. Now I have a quadratic. I can move everything to one side and factor. I'm going to move everything to the left so that my squared term is positive. If you don't like seeing it like this, you can rewrite this as 2y squared minus 7y plus 3 and factor it like that. I wouldn't use x's because there's an x in the question. So we're replacing all of our sine x's with a y, and then we're going to have to go back and put it back in after we factor. So to factor this, again, some of you might have different ways of factoring. This is the way I like because there's no guessing. It works every time. It's called decomposition. So I'm figuring out what are two numbers that multiply to be 6 and add to be -7. And my two numbers are -6 and -1. And so I break that middle term down into -6 and -1. And then I'm going to group the first two terms and the second two terms together. In my first two terms, my common factor is 2y, and then I am left with a y minus 3. My second two terms, I'm going to take out a -1, and then I would also be left with a y minus 3. That means my two factors are the 2y minus 1 here and the y minus 3 in the brackets. You do not have to factor this way. If you have another way of factoring, you are welcome to use that, but you should get the same two factors. If you don't have the same two factors, something didn't work and your method is flawed, or you didn't do your method correctly. So just be careful. You do need to know how to factor. You are expected to know how to factor a quadratic. So if you're not getting the right answers there, you might want to be reviewing that prior to going to university next year or going into calculus. So now that we're done, I'm going to put my sign back in because I didn't have a y in the question. I had a sine x in the question. And now I have my two solutions. I have that sine x, 2 sine x minus 1 is 0. Or I have that sine x minus 3 is 0, which means sine x equals 3 or sine x is equal to 1/2. So a reminder, sine x cannot be bigger than 1. So this one leaves us with no solutions. Sine x cannot be 3. There's no x that will work there. But our other answer, we know that sine is positive in quadrant 1. Quadrant 2, sine is opposite over hypotenuse, which makes my other side √3 and makes my reference angle pi over 6. Again, the question says in radians, so we have to use pi over 6, not 30 degrees, which means in quadrant 1, my x is going to be pi over 6 plus 2 pi n, where n is an integer. And in quadrant 2, x is going to be 5 pi over 6 plus 2 pi n, where n is an integer. None of these are my non-permissible values. My non-permissible value was 0, pi, 2 pi, etc. So we get to keep all of our solutions here, and we are done this question. And that is it. That is our extra section 6.4, which is basically solving equations from chapter 4 over. Again, the only new part here would be this first step of noticing that we need to replace our cosecant with 3 over sine x. And for example, in number 2, replacing the sine 2x. I've got number 3 replacing the sine 2x. Number 2 would be replacing the cotangent. And number 1 was, we've got the Pythagorean identity for 1b and cosine double angle identity for 1a. So once you've replaced those identities, you're just proceeding as you were in chapter 4. And that is all for today.